Hello everyone and welcome to Lecture. Today we'll be talking about how to more exactly define stability of both linear and nonlinear systems. So what we'll do is first review a couple important properties and definitions that we've talked about a little bit before, but I want to just emphasize again. So this will be stability of a nonlinear system of autonomous ODEs. So recall that a first order system is a system of form where xi 1 to xi n is a vector valued function and xi prime is equal to some function of xi. Where we have some initial condition in general, xi at t naught is equal to xi naught. So in this section we'll analyze the stability of such a system. We'll call this initial value problem star, where G is continuous function of xi1 through xi n, and G has continuous first order partial derivatives. And in general, because the solution is going to depend on the initial condition, we'll use the notation xi of t xi naught to denote the unique solution to start. Recall how we define the orbits as different a collection in Rn of all of the trajectories of this system, which partition Rn. And a very important property for us when we're discussing stability is a property of orbits called the semi-group property. And I'll describe this before I write it down. The idea is that for any orbit of our differential equation, let's say this is xi naught, the initial condition of the orbit along one of the orbit. This is, say, the solution at time t plus tau corresponding to initial condition xi naught. We can go back to xi of tau comma xi naught, and if we consider the new orbit, so we know that xi of tau comma xi naught is going to follow this orbit right here. If we start with the new initial condition, which is this right here, and follow the orbit, we're going to end up exactly, and the entire orbit itself is the same as this point right here, because xi of t and t naught are arbitrary, t and tau are arbitrary. This is we can choose any point t and tau on an orbit, but this point right here has to be equal to the value xi of t comma xi of t comma xi naught, right? Or the solution along the orbit starting at this point as an initial condition. This is relatively straightforward to prove, and it uses the uniqueness theorem, but written out it just says that let xi naught be an initial condition in Rn, and let alpha to omega in Rn be the maximal interval of existence. Then xi of t plus tau starting at initial condition xi naught has to be equal to xi of t starting at the initial condition xi of tau xi naught. For all points t, tau, and t plus tau in the maximum interval of existence. The proof of this is in our book. It uses the uniqueness theorem. The idea is that we can directly go through and utilize this idea along with the definitions that we worked on earlier for stability to go through and classify the stability of all linear systems, and we'll even see what we go to nonlinear systems that can be linearized, which is true as long as G has these continuous first order partial derivatives on the domain that we're interested in. So let's recall the definition of stability. And I introduced this concept earlier using norms, right? And I'll just rewrite these definitions right now. Let P star, psi star be some point in Rn. We define the open ball centered at xi naught with radius of epsilon is the set of points. We'll denote this as b of xi star, comma, epsilon. And it's the set of points xi in Rn such that the distance or norm of between xi and xi star, the norm of xi minus xi star, is less than epsilon. So if xi star is a point right here in n-dimensional space, we can draw a ball of radius epsilon around xi star, where the distance between any point in xi star in this ball is going to be less than epsilon. So this is saying, so if you remember how we define stability, this is the same thing as saying if xi star is an equilibrium point of the ODE or initial value problem star, then xi star is stable if for each epsilon ball surrounding xi star there is a delta ball surrounding xi star such that if an initial condition is inside the delta ball, then the solution to star with initial condition xi naught stays inside the epsilon ball, or for all t greater than or equal to 0. This is saying that for any epsilon, no matter how close you want to get to xi star, we can find some set of initial conditions, which is the delta ball, such that for points that start in here, initial conditions in the delta ball, the solution may leave the delta ball, but it'll always stay within the epsilon ball. If in addition to 2, there is another delta value, delta naught, possibly much smaller, such that for every initial condition in the delta naught ball, the limit as t goes to infinity of xi of t starting at xi naught is equal to xi star, then xi star is asymptotically stable. This is what we call it. So this 2 is stability, gives us the definition of stability, and 3 gives us the definition of asymptotically stable for a system of n nonlinear ODEs. And then if xi star is not stable, and we turn this unstable. And like I said before, when I introduced the concept of stability, we have other concepts of stability we can introduce, such as semi-stable and several different ideas here. But for us now, this is going to be the concept of stability that we're going to work with. So let's start by discussing the simplest type of system that we can think of, moving up from 1D, which is a 2x2 constant coefficient say stability of the equilibrium points of a so we're going to deal with systems of the form xi prime is equal to a xi, and we're going to focus on the case where the determinant of a is non-zero. A 2x2 linear system is going to be of the form x prime, y prime, is equal to A11, A12, A21, A22. And we have a number of different things that we want to think about here, but we remember from linear algebra some of the very nice properties that we have. Well, first off, we know that the characteristic polynomial of this is generally very important for determining solutions, because we need to find the eigenvalues of this matrix. So we need to look at the determinant of A minus lambda I, which is A11 minus lambda, A22 minus lambda, minus A12, A21, which ultimately results in the characteristic polynomial being lambda squared minus A11 plus A22 times lambda plus A11 A22 minus A12 A21. And this characteristic polynomial is invariant, which is one of the reasons why the coefficients of this characteristic polynomial are so important, and we have special names for each of the coefficients. This, you'll recall, is the trace of the matrix A, or the sum of the diagonal values of A, and this right here is called the determinant of the matrix A. We use both of these a decent amount of times already, but these values are invariant for any matrix A, and there are special values associated with the matrix. So we're going to call both of these P, we'll call it trace P, and we'll call Q the determinant of A. So for a 2x2 linear system, or 2x2 matrix A, the characteristic polynomial can be written as lambda squared minus P lambda plus Q. And we know that to get the eigenvalues, we have to look at the roots of the characteristic polynomial from the quadratic formula. These then give us that P over 2 plus or minus 1/2 times the square root of P squared minus 4Q, a value which is called discriminant and sometimes given the symbol delta. It's the P squared minus 4Q. Important thing to point out, and this is, this quadratic characteristic polynomial is specific to a 2x2 matrix, but the idea is that in general, for a 3x3 matrix or a higher degree matrix, the coefficients of the characteristic polynomial are the invariants of the matrix, and all the stuff that we're doing here can in practice be done for a higher dimensional system as well, but things become a lot more complicated. However, we can do this in practice if we so desire. It's just going to take a little bit more work. So the idea here is that you can always write, and this is also something that is true in general for matrices, write the trace of a matrix as the sum of its eigenvalues, and the determinant of matrix can always be written as the product of its eigenvalues. And what this gives us is, after seeing what we've seen so far about getting solutions to homogeneous and inhomogeneous constant coefficient systems, we now know, right, how to go through and actually determine what the solutions are going to look like for various values of P and Q, or lambda 1 and lambda 2, or for the eigenvalues of a given matrix. Remember that we're assuming that through all of this, the determinant's non-zero. The analysis will be different if the determinant is equal to 0, because Q will be 0. However, the first thing that we want to note is that when the determinant is non-zero, we will only have one equilibrium point, which will be the origin. And the reason for that is because when you go to solve the equilibrium point, you end up solving a matrix system of the form A times xi equals 0, which, if the determinant is non-zero, has one and only one solution, which is the solution 0, 0. This also holds for any n by n system as well. If the determinant is equal to 0, then there will be infinitely many solutions to this homogeneous equation, the homogeneous system. So this is why we have to be a little bit more careful when the determinant's non-zero. However, so let's go through and try and classify these critical points, or we'll try and classify this equilibrium point under various circumstances. So the first circumstance is the case of p squared minus 4q is less than 0. So if the discriminant delta is less than 0, and we actually have 3 subcases that are all different here. The first is p less than 0. The second is p equal to 0. And the third is p greater than 0. When p squared minus 4q is less than 0, we have distinct, complex eigenvalues lambda 1 is equal to alpha minus beta I. For real numbers alpha and beta, we have lambda 2 alpha plus beta I, and u is equal to a minus I times b, and v is a plus I times b as the eigenvectors corresponding to those distinct eigenvalues. And in each one of these cases, we also have that the solution xi of t is of the form e to the alpha t times c1 a cosine of beta t plus b sine of beta t plus e to the alpha t times c2 b times cosine of beta t plus a times sine of beta t. And we showed this a few lectures ago. But this directly tells us exactly what happens in terms of the stability of the critical points for each of these possible scenarios that I just listed over here. And we can see that directly when we kind of think about how this solution is going to be behaving, right? You have here the x and y values are going to be a complicated function of possibly sine and cosine of beta t, and oops, sorry, this should be a negative 1 right here, minus a sine of beta t. But this is the general form for solutions for either of these two cases, and we'll see that the shape of solutions is directly determined by this functional form right here. We know that when p squared minus 4q is equal to 0, that this corresponds to the case of having one eigenvalue which actually results in two possible cases for us to go through and look at. We can have still p be less than 0, or p be greater than 0. You could also consider p equals 0, but that would give you the determinant equals 0, which we're not looking at right now. So, because of the fact that this equals 0, p squared minus 4q is equal to 0, in this possible case, the discriminant will be 0, so the eigenvalue lambda is going to be equal to just p over 2 itself, where p is a real value. And this generates then two cases that we have to consider. So we have a repeated eigenvalue, we'll say lambda 1 is equal to alpha, and lambda 2 is equal to alpha. If we have two linearly independent eigenvectors for that one eigenvalue, the solution is called a proper node, or I should say the critical point is called a proper node. Because the solution is of the form xi of t is equal to e to the alpha t times c1 times u plus c2 times v, where u and v are the two linearly independent eigenvectors. In the event that we only have one eigenvector, the solution is called an improper node. And if that eigenvector is u, when we go through and solve the system using the method that we showed the other day, using the matrix exponential, the general solution will end up breaking down to e to the alpha t times c1 u plus c2 times tu plus xi plus eta, vector eta, where eta is called a generalized eigenvector and comes from the process described in the last lecture, when we, for solving a linear system, when we have repeated eigenvalues. So this is the second case. And the last case is going to be if we have distinct real eigenvalues. This is when p squared minus 4q is less than 0, or is greater than 0. So we'll call this is 1, 2, 3. We'll say this would be 4, 5, and then we have 3 situations here. We could have P be less than 0 and Q be greater than 0. We could have here P be greater than 0 and Q be less than 0. And we could have Q just be less than 0. So these are the main distinctions we have to make here. So in this scenario we have distinct, real eigenvalues for the matrix A. Lambda 1 U and lambda 2 U are the eigenpairs. In the general solution form we found was just xi of t is equal to c1 e to the lambda 1 t times u plus c2 e to the lambda 2 t times v. And the reason that we are including q here is because if this is greater than 0, this means that q is less than p squared over 4, which means that the two main potential values for q that we have is q could be less than 0 and q could be greater than 0 in this region. Same thing, right here, p squared minus 4q is equal to 0. This just means that q is equal to p squared over 4, so q has to be positive for any of these points. And same thing here, when p squared minus 4q is less than 0, then q has to be greater than p squared over 4, which means that q is necessarily positive. But so we have the fundamental solution, or the solution form, in each one of these scenarios, and so if we take this right here, and I'll just copy all of this down and discuss what the solutions look like for each one of these cases. P is less than 0, and p squared minus 4q is also less than 0, we know the solution is going to be like this, and p being less than 0 implies that 2 times alpha is less than 0. because of the fact that P is lambda 1 plus lambda 2, and in this case the eigenvalues are alpha minus beta I and alpha plus beta I. So this means that alpha is negative in this solution right here. As time goes, it's larger and larger and larger. E to the alpha t is getting smaller and smaller and smaller, but your x and your y's are still dominated by sines and cosines. So the solution form is what's called an asymptotically stable spiral. Which will look kind of like this as the solution, and this will happen everywhere for every given initial condition, decays down to the critical point. When P is equal to 0, we have what's called a stable center. Because looking at our solution right here, when P is equal to 0, that means that 2 times alpha is equal to 0, which means that in our solution form you have e to the 0, e to the 0, which is 1, and so we have the orbits are going to be elliptical in general around a given point, or on the equilibrium point of the origin. So the orbits generally are going to look like this. And the third possibility that we have here is called an asymptotically, or just an unstable spiral. Because of the fact that alpha will be positive, so any solution will be growing without bound and spiraling away due to the fact that the eigenvalue alpha is positive, so these are exponentially increasing. So the direction of these orbits are going into the origin here and out of the origin for this spiral. Because this is when 2 alpha is positive. And that exhausts all possible solution types for this this region. For the proper node, we'll have that the solutions for a proper node and an improper node differ qualitatively. Proper node, or a star-shaped node, as it's sometimes called, has this solution form right here, e to the alpha t times c1u plus c2v, the solution of which will always point along, right, in a direction that's decreasing if alpha is negative and increasing if alpha is positive. So we'll always be going linearly into the equilibrium point. If alpha is negative, in which case it's called a stable proper node. This is when this eigenvalue is less than 0, or P is less than 0. And an improper node, where we only have one eigendirection, is going to look a little bit different, and the eigendirection is actually called the stable manifold when P is less than 0. It's along the eigendirection U. And if this is the origin, solutions of this form spiral in and approach a tangent along this stable manifold. And likewise, if we have stable proper nodes and stable improper nodes, we also have unstable proper nodes and improper nodes as well. These are pictures that look essentially the same. But are moving away. From the equilibrium point. For an unstable improper node, we also have an unstable manifold, it's called, because on this manifold the eigen directions. Any solution will come in and stay along this direction right here. Same thing for an unstable improper node. The solutions will be spiraling away in general from this critical point, tangent to the unstable manifold. In each of these cases, right, you can very clearly see by plotting out some representative trajectories that this is what you'll end up getting. It's very, very clearly done out in our book as well as in many other books. So the last case here that we have to consider is the case of distinct real eigenvalues. And in the first case, when P is negative and Q is positive, the general solution form gives us, well, this is our general solution form, and if P is negative and Q is positive, well, that's going to mean the following: that lambda 1 and lambda 2 will both be negative, and therefore we will get what's called an asymptotically stable node. And this type of node is characterized by the solution direction always going in towards the equilibrium point. And in general, we have two distinct eigenvalues, so we'll have two distinct eigendirections here. Or two stable manifolds corresponding to the eigenvectors u and the eigenvectors v, where the solutions will come in straight lines along these eigendirections. However, for any initial condition not on one of the eigenaxes, solutions will come in on exponential curves of varying change. So we'll just draw 4 like this. If P is greater than 0 and Q is still less than 0, then we have this exact same picture. However, the only thing changing is that the solution direction will be moving away from the node. We call this an unstable node. And just like before, we'll have two manifolds, or collections of points here, corresponding to the eigendirections, where the solution will be moving in a straight line, but it'll be moving away from the equilibrium point. And for every other initial condition, the solution will be moving away from the equilibrium point along exponential curves that look like this. So this is called an unstable node. And the last possible case is what's called a saddle point, which is also an unstable saddle point, just to emphasize that. And this is the case of having a positive eigenvalue and a negative real eigenvalue You have two eigendirections. One eigendirection is a stable manifold, and one eigendirection is an unstable manifold. Along the stable eigendirection, the solution will be moving in to the equilibrium point. But in the unstable eigendirection, the solution will be moving away from the equilibrium point. So for initial conditions off, not on these eigendirections, the orbits will move like this. Hence the name saddle point. Okay, and this summarizes all of the possibilities that we have for a 2x2 linear system. I should say linear constant coefficient system. Because certainly if the coefficient matrix is variable, then we have things that will be changing. We have to think a little bit harder on how we would classify critical points. But what's amazing about this is that we can classify all of these types of solutions as all of the solutions, and not only that, we can actually very nicely visually represent what each one of these solutions means in two-dimensional PQ space. So if we draw a p-axis and a q-axis, and we draw out the relationship p squared minus 4q equals 0 on the p-axis and the q-axis, what we end up seeing is the following picture. And let me just copy this right now. So I just plotted this out in Desmos so you can get an idea of what this looks like here. And let's make this a little bit, bring this all a little bit up so we have a little bit more room here. So this curve right here is the curve p squared minus 4q is equal to 0, where this is the p-axis and this is the q-axis. And we have very clearly that unstable spiral away from the origin is this region. This region is asymptotically stable spiral to the origin. On the curve we have asymptotically stable nodes, unstable nodes. When p is negative, but we have that it's below, so 4q is below p squared. We have an asymptotically stable node, and when q is negative, we have an unstable saddle point. And then when p is 0, we have a stable center, and q is positive. But this is quite incredible. And the idea now is that I'm not going to go and do this for every n by n system. What we are just going to take a look at what happens for the stability of linear constant coefficient homogeneous systems in general, for an n by n linear constant coefficient homogeneous system. Just take a look at what the given matrix solution implies. So we can go through and do this very nicely.